Okay, thank you, Kirill, for the invitation to come here and for this opportunity. So as Kirill mentioned, I work at Station Q, Microsoft Station Q. It's a big effort which encompasses people doing computer science, mathematics, theoretical physics, experimental physics, and engineering. And our mission is to build quantum computers. In particular approach that we take to building quantum computers is through this topological approach, which was the idea that we want to build qubits that are protected at some level, at the fundamental level, by laws of physics rather than by using computational error correction. So the title of my talk is here, and here's also the outline of my talk. I'll review experimental progress, theoretical and experimental progress over the last 8 years, and towards the end of the talk, I'll show you some future proposals and explain some ideas how we can use Majorana zero modes to build quantum computers. So if you look at different realizations of qubits, they can be divided in two classes. So in the first class are these microscopic qubits. These are qubits that are based on microscopic degrees of freedom. So one is trying to isolate a spin, say, of a nuclei or a charge of electron and control this two-level system and bring the system to desired quantum state. The second category of qubits is based on collective behavior of electrons. And the first example is a well-known example in superconductivity, where the phase of superconductor described the motion of billions of electrons altogether. And in some sense, the topological approach is based on qubits. It's the extreme limit of this collective behavior where information is encoded as a gross geometry rather than microscopic degrees of freedom. And that has certain advantages, as I explained down the road. So the idea of using topology in quantum computing, for quantum computing applications, goes back to Alexei Kitaev, who actually realized a very important fact that, if you look at this rope, and if you look at this rope locally, it doesn't tell you anything about its gross geometry, right? It doesn't tell you that there is a knot in this rope. And if we encode information in gross geometry of this manifold, right, and the fact that the system has knots or not, then noise, which predominantly acts locally, will not be able to disrupt information, will not be able to read off the information that's encoded in the system. So that's, in a nutshell, the idea. So more precisely, what we try to use, we try to first find topological phases of matter. These are very specific phases of matter. They're called non-abelian phases of matter. And then we try to manipulate certain excitations in these phases of matter, which are called anyons, non-abelian anyons. And by doing certain non-local manipulations over the degenerate manifold in this topological phase of matter, one can do quantum computation. Okay? So, and the main advantage of topological quantum computing is that the system is intrinsically protected. It's protected at the hardware level rather than, as opposed to conventional qubits, and these are driven two-level systems, in which case, excited state of the system always decays, and one has to always worry about correcting errors and build certain schemes, use certain error correction schemes to do error correction. Okay, so what's the basic idea? The basic idea goes back to the fact that unlike in 3 dimensions, in which case exchange operation is trivial in the sense that it gives you just either plus or minus, and we know that because we know that in 3 dimensions we only have electrons and bosons. But this fact actually goes back to a simple fact that if we do the exchange transformation in 3 dimensions, we have this freedom in z direction to reduce this loop to a point. And if we reduce this loop to a point, if we exchange it twice and reduce loop to a point, that means that we didn't do anything on the system. That means that the transformation t squared, and t being the exchange transformation, has to lead to just 1, has to be equal 1. And therefore, the square root is equal to plus minus 1. But in 2 dimensions, the situation may be different because we don't have this degree of freedom to shrink the loop to 0, because if there is some singularity in 2-dimensional space, then this singularity will not let us go around it. So in 2 dimensions, there are 2 different possibilities. Well, first of all, t doesn't have to be equal to t minus 1 for the fact that I just mentioned that clockwise and counterclockwise exchanges can be different. And this was first pointed out by Lena Smerheim and Frank Wilczek. But this fact leads to abelian statistics, and it's well known from fractional quantum Hall community, in fractional quantum Hall community, that exchange of quasi-particles, say in nu equal 1/3, leads to some non-trivial phase, which is not equal 0 or pi. Such exchange transformation leads to some phase. This is very interesting, of course, fact to show that there's different statistics than just bosons and fermions. It has fundamental implications for for all of physics. But actually, what we are trying to achieve is something even more complicated. We're trying to realize a system in which exchange transformation, rather than give you just abelian phase, acts as a matrix on some degenerate manifold. So prerequisite for the system is to have degeneracy in the system, massive degeneracy in the system. And in that case, if we do certain manipulations, certain non-local manipulations in this degenerate manifold, the idea is that these manipulations may actually act as a matrix within this manifold. So this is maybe to explain what I'm trying to say. So rather than having just a phase, exchange of particle 1 and 3 will lead to the same matrix M. An exchange of particle 2 and 3 will lead to some matrix N. And if these 2 matrices do not commute with each other, that means that we can manipulate information. So that's the basic idea of topological quantum computation. And there's fundamental difference with respect to conventional computation, because here we always deal with the ground state manifold. So in this scheme, we never invoke excited states. We only deal with ground state manifold. Okay, so the skeptic in the audience will say, well, where do we find these systems in nature? This sounds great. So topology in real life. So in my building, in the building that Station Q is located, we have Media Arts and Technology group, and we have Station Q group. So when you walk along the halls of Media Arts and Technology group, you often see these kind of images, which go back to Asher, and it goes back to early 20th century. So actually, these guys were ahead of us. And the applications of topology in condensed matter started basically in 80s, with realizing that integer quantum Hall effect is related to TKNN number, which is topological invariant. And if you measure Hall conductivity in two-dimensional electron gas in strong magnetic fields, then you find that the measured quantity, Hall conductivity, is quantized to very high precision, to 10 to the minus 9. And it's independent of disorder, independent of the shape of the sample, independent of many microscopic details. And then people realize that the reason it is so precisely quantized, it has to do with this topological invariant. And then as we move on, this is progression, which culminated with the Nobel Prize in 2016 for, in particular, one of the achievements for which it was acknowledged was for realizing topological insulators, which is an interesting phase of matter in which, again, the bulk structure has some topological invariant in it. So the phases that we care and we would like to realize are more complicated phases, as I mentioned, and these are the candidate systems which are known. So the first class has this intrinsic origin. It's certain superconductors where ingredients are such that we know and we suspect, and theory predicts that there is a realization of this interesting superconducting state or interesting fractional quantum Hall state in which there is ground state degeneracy. And actually, until mid-2000s, this was the status of the field. So these were the two prominent candidate systems in which scientists were trying to find topological states of matter with non-abelian statistics. However, with discovery of topological insulators, we realized that one can engineer Hamiltonians using interface physics. So essentially, one can condense the necessary ingredients that are important to realize, say, certain exotic superconductors. They're called P-wave superconductors because their spatial wave function, two-body wave function, has this P-wave character. And P-wave means that it changes the sign if momentum goes P to minus P. And we realized that such a superconductor can be engineered at the surface of certain materials. And today, I will talk about these materials, proximitized nanowires, which are shown here, which consist of semiconductor with Rashba spin-orbit coupling and S-wave superconductor. So I'll show you that, if you combine ingredients in the right proportions, even those materials are very simple, but if you combine these ingredients in the right proportions, one can realize a very interesting exotic state of matter. Okay, so first, let me try to explain how spin-orbit coupling emerges in two-dimensional structures. It emerges because you have inversion symmetry breaking at the interface of, say, semiconductor and some other material. And essentially, that results in a strong electric field that appears in the system. So here's electric field. The motion of electrons is confined to two-dimensional plane. And so it turns out that it was shown that you have a term which is proportional sigma cross P. The way to understand this term, if I massage this equation a little bit, I can go to a rest frame of moving electron, and I can show that this Hamiltonian can be obtained just by saying that in the rest frame of electron, there is Zeeman splitting of an electron, which is momentum dependent. Okay? And that's how Rashba spin-orbit coupling appears in the heterostructures. So if you just consider a typical dispersion of such Hamiltonian, which has p squared over 2m, just a conventional expansion around the bottom of the band, and then you add this Rashba term, this is basically the dispersion that you will find. And the idea is that one finds two Fermi surfaces. So there is a small Fermi surface, and there is large Fermi surfaces. Or if you wish, one can also think that there is a momentum-dependent shift or spin-dependent shift of the Fermi surface. For spin up and spin down, you can shift the surfaces either to the right or to the left, and that's the structure that we'll find. Okay. This is the effect of Rajba spin-orbit coupling. So now let me just take this semiconductor, confine it to one-dimensional structure, and consider the following model. So again, this is just a parabolic term. This is chemical potential. This is Rajba spin-orbit coupling. We confine the motion in y direction, and only motion in x direction is left. And we also will apply magnetic field, which is proportional to this term. Okay? So this part over here describes the Hamiltonian for semiconducting wire. And then if you place this semiconducting wire in intimate contact with superconductor, electrons can tunnel into superconductor only in pairs, because superconductor penalizes single particle excitations. So therefore, the term that describes such disappearance and appearance of electrons in pairs is given by the second term in this Hamiltonian, and that's what we call proximity-induced superconductivity, which appears when you have a normal metal close to a superconductor. Okay? So this is the model that actually will lead to exotic superconductor, as I will show you. And this exotic superconductor will support Majorana zero energy modes. So to see that, we can just look at the semiconductor part and try to diagonalize this part. And in order to diagonalize this part, one can notice that spin-orbit coupling does not commute with Zeeman term. And that means that in this shifted parabolas picture, we will have a gap at zero momenta, which is shown here. And if we take and tune chemical potential to be in the middle, then you can see that we realize something very interesting where there is spin momentum locking. So right movers are locked with spin up, and left movers are locked with spin down. This is so-called helical liquid, where the motion is coupled to spin. But in a sense, we took care of the spin degeneracy that always appears in the absence of Rajba spin-orbit coupling and Zeeman field, and we reduced the state with two Fermi surfaces to the state with a single Fermi surface. And single Fermi surface means that we just have one species of particles. It's just one Fermi surface. And then in this basis of diagonalized states, we can look what happens with the second term, which is a P wave, which was induced by S-wave superconductor. And one can just project out this excited band, assuming that chemical potential is in the middle. So we'll just leave psi minus particles in the lower subband. Then I will just cross out all the terms that appear in this pairing potential and leave just one. And because this one is proportional to just a single species, and fermion anti-commutation relation forces this coefficient delta P to be odd in momentum. So basically, what I'm trying to say is that we started with S-wave superconductor with pairing where delta is a constant, and we used spin-orbit coupling to enslave spin degree of freedom and used magnetic field to break time reversal symmetry. And then, when we combined all these ingredients together, we realized actually at the interface a P-wave superconductor where pairing potential is proportional to momentum, which was different than the superconducting state we started with. Now, so these are requirements for materials. So materials should have obviously large spin-orbit coupling. We also would like to have large G factor in semiconductors so that this term will be appreciable. And we also want good contacts with metals so that this induced gap will be large. And that's it. These are garden variety semiconductors, which been studied in condensed matter for the last 50 years. And we know a lot about the properties. We can tune density, we can tune chemical potential. So what happens in such a system? What happens is that if you just take this Hamiltonian and put on the lattice, then you will find that there are two phases as a function of magnetic field. So this is a trivial phase in which the system behaves as if it was like S-wave superconductor. And then there is a topological phase shown here, which the system behaves as if it was a P-wave superconductor. And to see that explicitly, we can just solve on a lattice this Hamiltonian and look at density of states. So if magnetic field is such that it's here, then what you find is a function of the length of the system and energy, that there are no states below the gap anywhere. Okay, so it's just gapped, and these are continuum states. And if you cross this boundary, then you'll find that there are these zero energy states, near zero energy states appearing in the system, which are localized at the opposite ends of the wires. Okay, and this is fairly generic. Once we put chemical potential in the middle of the gap, small changes, small deviations of parameters do not change this picture. Okay. This picture is guaranteed by topology. So the presence of these zero energy states is guaranteed by topologies of the bulk. Okay, and that's a very important point because it guarantees the stability of the system. So an important point is this overlap between two Majoranas. Because it's a gapped system, this overlap between two Majoranas will scale exponentially as a system length. In a gapped system, we have decay of the wave functions, which goes exponentially with length, and the same is true here. And I'm going to use this fact for topological quantum computing, that if you manipulate these Majoranas, and as long as they are separated by distances larger than certain length scale, which in this case is the superconducting coherence length, then their overlaps, their energy splitting is exponentially small. Okay, so suppose you realize such a system, right? How do you check that at the ends of the wire we have these zero energy states? Well, the simplest recipe is that, look, you just tune magnetic field, and if I have density of states at zero energy, I can just tunnel with STM into the end of the wire, and I should see a peak at zero bias. Okay, so transport experiments are very sensitive probes, and they can, with higher resolution, tell you whether you have zero energy state at the end or not. So indeed, if you look at the calculation, simple calculation for conductance, the IDV, differential conductance, then you find that if the system is topological, then this conductance scales approaches 2 is equal to h, whereas if it's non-topological, it goes to 0. So it's a very simple signature. Now, the signature actually appears because there is a resonant scattering at the interface between normal electron and between normal metal and superconductor. So in such interface, there is a process in which electron incident on the surface gets reflected as a whole, and has to do with superconductivity here. Whenever such process happens, a Cooper pair gets transmitted into condensate. It's called Andreev Reflection. Okay? And if you have a state exactly at zero energy here, then there is a new phenomenon. It's called resonant Andreev Reflection, which resonant because such Andreev reflection happens with unit probability at zero temperature, regardless of the barrier that may exist at this interface. Okay? And this is actually a very robust statement. It has to do with unitarity and particle hole symmetry of the scattering matrix. So scattering matrix, which characterizes transport, is heavily constrained by these two conservation laws. And we only have two solutions in this case at zero energy. Okay? There is one solution which is called perfect normal reflection, in which electron comes in and gets completely backscattered as an electron. That's one possibility. And the other possibility is that you have an electron coming in and gets reflected as a hole. And in this case, you have a different boundary conditions. One can also express it in terms of scattering matrices. So which tells you that there's certain discreteness at zero energy. It's either one or the other. And because of this discreteness, the low temperature transport actually will plateau at the quantized value of 2e⁻⁸h. And so this is the signature that we are looking at. We are looking at transport experiments in which tunneling at the end will give us peak at zero bias, but moreover, as we change the barrier and lower the temperature, this feature should be robust and should plateau at 2e⁻⁸h. And that would be the signature of the presence of these Majorana zero modes. So the first experiments that attempted to measure the presence of these zero energy states were done in Delft by Leo Coulomb group. So they took indium antimonide wire. This is a superconductor, niobium titanium nitride, and this is gold, and there are a bunch of electrodes underneath. And so this electrode somewhere in the middle tunes the barrier in the system. These electrodes over here are supposed to tune density in the wire, and one can try to tune it to the right regime and then change magnetic field and see whether there is zero energy state appearing as a function of the field. So here is the data. So in this data, you see indeed that at zero field, there's nothing at zero bias, but then you have a peak appearing, and this peak appearing and persisting over large values of magnetic field. So actually, in terms of energy scales, this is very appreciable range in terms of energy scale. So Zeeman energy was changed by a few kelvins, whereas the temperature was 50 millikelvin. Okay. So that seems like a positive signature. However, there are other features that one could argue that are inconsistent with the simpler prediction, and especially this background and the softness of the density of states. So initial data was mixed because there are certain features that are very consistent with the theory, but there are certain features that are inconsistent with this theory. And very quickly we realized that actually it's all about material science. It's all about developing material science and cleaning the system and trying to reduce the amount of disorder in the system. And so the further developments have to do with the fact that we learned how to make very clean interfaces between these two materials. So here is a structure that was grown by MBE by Peter Krogstrup from Copenhagen, where he took these indium arsenide wires and he deposited aluminum on them in the MBE. So this epitaxial deposition yields a very nice and very clean interface. And one can immediately see that after this material science breakthrough, we have very different signatures in transport. So if you look at the conductance as a function of applied voltage bias, then you can see that these features are very sharp rather than smooth, as I showed before in the previous slide. And very quickly, we also learned that in indium antimonide wires, we can do the same trick. We can improve material science of the interface, and the signatures will look much cleaner. So once this happened, this material development happened, we could see the effect that we care. In particular, quantization of the conductance and appearance of zero bias peak at magnetic field. So this is the data from a very recent experiment, again in Delft, by Covenhoven's group, in which you apply magnetic field. So this is magnetic field, and there's a gap closing, and then appearance of zero energy state, which correspond to Majorana modes. And you can also see that if you look at the magnitude of the peak, it reaches quantized value of 2e squared over h. And there is a test that one can do, because I told you that this peak is robust with respect to change in the tunnel barrier due to this resonant Andreev reflection. So what you can do, you can basically change the barrier, and this is done here. So you change tunnel gate voltage, which changes the barrier height, and then you look at the change in the conductance above the gap at finite bias, and you look at the change of the conductance at zero bias, which probes the presence of the zero energy state. And you can see that conductance at zero bias stayed around quantized value, whereas conductance at finite bias changed by a factor of 2 or 3. So we are significantly changing the height of this tunnel barrier, but this feature is robust with respect to such variation. So this is really a strong evidence for the presence of these Majorana zero energy states at the end of the wire. Okay, so so far I was talking about systems in which aluminum is only deposited over fraction over two facets of this hexagonal nanowires. And the reason it's done this way, because we would like to tune density, and so therefore we would like to apply electric field from the opposite side, because aluminum screens the electric field. But very recently we've done experiments in, well, let me maybe skip these two slides. We've done experiments in which the aluminum was deposited around the whole shell. So these are so-called full shell wires. So here's aluminum shell, and this is the indium arsenide shell. And one can show that the same physics is realized in these full shell wires, but because of orbital magnetic field rather than Zeeman magnetic field. So remember, the Zeeman field acts on a spin degree of freedom, whereas orbital orbital effect of magnetic field acts on a spatial wave function. And one can show that the presence of spin-orbit coupling and this orbital field will conspire to the same physics. It's actually quite an interesting experiment. So if you just take a hollow superconducting shell, this physics is well known in condensed matter. It goes back to Little Parks. And Little Parks showed that if you have this hollow cylinder and you apply magnetic field along the direction of the cylinder, then there is modulation of the gap. And this is shown here. This is actually theoretical simulation for this system. And we understand the magnitude of this modulation. However, if you take and have a semiconducting core in the system and put a superconducting shell, then there is something interesting that happens. So at zero magnetic field, so winding number around superconducting phase winding is zero magnetic field, you see similar signature. You see that there are no subgap states. It's very nice, clean density of states. But as you apply a flux, which is, if you apply a field which is proportional to a flux quantum through this system, then you see that there is a gap and appearance of zero energy state. And this motion, orbital motion of electrons around the circumference, actually in some way is equivalent to presence of Zeeman field in the system. And we've done theoretical simulations for this system, which I'm not showing here, but I'll show you just the results. And if you're interested, I can talk about details, in which we do confirm the presence of these zero energy states in the system exactly at the absence at n equals 0 and the presence at n equals 1, where n is the winding of the superconducting wave function around the circumference. So this is, again, experimental data. This is the theory data. And we find consistent results with experimental measurements. So So that's exciting news because it opens doors to even more materials. So the only requirement we now have is the requirement for large spin orbit coupling. And we don't even need to have large G factor in these materials, because the role of Zeeman field in this system is played by the orbital component of magnetic field. So it effectively expands the number of materials that can be used to realize this physics. Okay, so an additional experiment which also tells us that we're on the right track can be done in finite superconducting islands. So here I showed all data. This data is from 1993 from Saclay group led by Michel Davoret, in which they studied how charge in this superconducting island, which is shown here schematically, changes as a function of the gate voltage applied to it. So because it is a superconductor and it's just an S-wave superconductor, if the gap is large compared to like charging energy, which is essentially electrostatic cost to add an extra electron to the system, in such a case, the ground state will be completely 2E periodic, meaning that the ground state will remain even regardless of the value of the gate voltage applied to a system. And that happens because if I look at the charging energy, which is quadratic in this induced gate charge, and in case the gap is larger than the charging energy, then the system just cycles between even parabolas. So these are even parabolas. And therefore, if you measure charge on such an island, it jumps in steps of 2E and just continues as a function of gate. Well, in the experiments that we would like to conduct with these proximitized wires that actually have been conducted with experiments in these proximitized wires, we can tune the gap. And in fact, we can reduce the gap to 0. The gap is closing at the topological phase transition, and then appears 0 energy state at the other side of the transition. So therefore, the signature, what we expect is that we start with a large gap, and then as a function of some field, the gap goes down. And so now the ground state will change from even to odd, even to odd, and to even. But then eventually, when we go through the transition, the ground state energy, this difference, this level will come down, and eventually the periodicity of the ground state energy becomes 1E. And that's because we have this pair of 0 energy states. These two Majoranas can absorb an extra fermion that is added to the system, and the system effectively doesn't care about parity because there is a state at 0 energy that can take up extra electron. Okay? So this is very specific prediction what mesoscopic topological superconductor should look like. If you have a small system and then you're adding electrons one by one and you have these 0 energy states, then the signature should be that you go from 2E periodicity to 1E periodicity as a function of magnetic field. So let's try to test this scenario as well. Okay, so this is a very new data which I explained on full shell nanowires. And what experimentalists did, they basically created many of these islands of different lengths. And remember, I told you that if you have these Majorana modes and they're at the opposite sides of the nanowire, then their overlap is exponentially small with the length of the wire. So we would like to test, we would like to measure this dependence of the overlap of the energy splitting on lengths. Therefore, they grew samples from 200 nanometers to 1 micron, and in each of them they measured 2-terminal conductance. So this first experiment, second experiment, and so on and so forth. And what they do as a function of magnetic field, they see that at 0 field, the spacing between, as a function of gate voltage, spacing is 2E, and that's at 0 field and 0 winding number. But then when they go to winding number equal to 1, the spacing becomes 1e, almost 1e. And there is certain leftover between, there is some certain difference between even and odd. This difference is small, and we would like to measure this small effect and try to see how it scales with the system size. Okay, so here I showed basically data for 200 nanometers. So this is how data looks like. So this is the difference between even and odd as a function of magnetic field. Even and odd spacing as a function of magnetic field. This is finite bias conductance, which show you that you have 2e, and then eventually you have 1e at 100 millitesla and 0 field. So one can repeat this experiment on and look at these differences between even and odd spacings. And then one can plot this difference between even and odd spacing as a function of length as a function of length on log-log plot. So if the dependence is indeed exponential in length, then we should see the data fall into this on the line in this plot. If you have some kind of extended state that, for which we expect to see dependence 1 over L, then we should see that it is extended state, and that's a different physics. And so what we find from these measurements, that indeed the line falls on exponential with very reasonable coherence length, which is of the order of 200 nanometers. So that's another evidence that we are on the right track in realizing these topological superconductors. Because A, we see that conductance is quantized. In NS experiments, B, we see that the splitting of the modes falls on this exponential dependence. So that's very encouraging news, because we can move forward and try to build qubits out of these systems. Now, I skipped a couple of slides, but let me go back to the idea. Just wanted to show you that how this can be done. So we can scale up this building of wires and use selective area growth technique, in which we make trenches, and in these trenches we grow wires on demand. And so here's the data showing that we can do it. So this is the lattice. This is a network of one-dimensional wires made of indium arsenide, and this is how the wire looks like. This is actually the aluminum, thin aluminum layer, which was deposited afterwards. So we can make networks of any shape. So here's another example of wires growing in different crystal direction, and again, we can grow different crystal shapes. So this nanowire approach allows one to use lithography to scale up to networks, and then use fabrication techniques to just fab the devices that we want. Okay. So what do we actually want to build? So we would like to build superconducting islands which have some ground state degeneracy. Now let me show you that when you have Majoranas and when you exchange the position of these Majoranas, one is doing something very non-trivial on the system. So I mentioned abstractly that that's true for some abstract state, that there is such possibility, but why does it happen for Majoranas? Okay, so just if you have ground state degeneracy, you can take a pair of Majoranas and form a conventional Dirac fermion, complex fermion. Okay, so let's just do that. So let's say gamma 1 and gamma 2 logically gets paired, and we introduce this fermion C. And then this pair over here can be either unoccupied or occupied. So it gives me a two-level system. I can do the same with gamma 3 and gamma 4. And then what I can do logically, since Majoranas are independent objects, I can exchange gamma 2 and gamma 3. But this exchange is, colloquially speaking, is equivalent to exchanging a fraction of one electron with a fraction of another electron. And we know that something like that doesn't happen usually in condensed matter physics. We cannot just take a fraction of electron and exchange it with another one. Okay? Now, well, this is all words. You can actually check that if you form, say, this four-dimensional Hilbert space, which are enumerated by unoccupied state A and occupied state B, etc., and do this exchange transformation, that actually it introduces a gate, and this gate is just shown here. So if you act with exchange transformation on this degenerate manifold of Majoranas, such an exchange transformation corresponds to a quantum gate. So in the previous, there were some ideas how to physically manipulate these Majoranas using networks of the wires, but I'll show you a different approach where one, rather than physically moving things around, and moving things around, you have to drag essentially very massive objects. We would like to rather do the measurements. So we do measurements, but these measurements are equivalent to exchanging things around. Okay? So this is so-called measurement-based quantum computation. Rather than moving things around, we can do measurements, but at the end of the day, a sequence of measurements will be equivalent to moving or exchanging these Majoranas. Okay, so what is the idea? The idea is very simple. It's shown here. We create a network of these semiconductor wires. We grow them, as I showed you that using this selective area growth technique, we can grow these networks. Then we deposit superconductors in the regions that we want. So this is gray color corresponds to superconductor. We know that this yellow color here corresponds to just a semiconductor, and there is a tunnel gate between superconductor and semiconductor region. So we can turn on and off the coupling between semiconductor and superconductor. And we also add just a trivial element, which is just aluminum bridge, which couples this part and this part. So when I do that, we've created an island with one two-level system here and another two-level system here. So it's four-dimensional Hilbert space. However, if we have a global constraint because of the charging energy, so charge is fixed, that means we have to reduce, we have to take into account this constraint. And from four-dimensional Hilbert space, we reduce to two-dimensional Hilbert space. So this object here will correspond to a degenerate two-level system. Okay? And this degenerate two-level system will be our qubit. So now, what do I need to do? I need to show you that we can manipulate this qubit. Now we have a degenerate two-level system, then we would like to manipulate the qubit. Okay, the way to manipulate is to use well-known effect in quantum mechanics. It turns out that if you have this system closed, and if you let these barriers, if you lower these barriers, but still keep them large, you just open the window to a topological system so that environment just weakly measures it. In second-order perturbation theory, one can show that quantum fluctuations of charge between semiconductor island shown here and these Majoranas, that they will be sensitive to the parity of two Majoranas. They will be sensitive to what is encoded in the product of gamma 1 and gamma 2. Okay? And this operation is actually a non-local operation because before the correlation between of the wave function between gamma 1 and gamma 2 was determined by this total distance shown here. But now if I open these barriers and I allow the charge fluctuate like this, then I'm basically providing a shortcut, okay, which will correspond to something non-local done on the system. So in other words, the process of electron tunneling here and then propagating through a system and then tunneling out on the other end actually corresponds to a little interferometer. And we know that interferometers, they are sensitive to, these are global quantities. They're sensitive what happens inside of this trajectory, and therefore they're sensitive to the parity of gamma 1 and gamma 2. So, and then if we have such process for one pair of Majoranas, one can show that we can also perform 2-qubit gates and couple 2 qubits through the same loops. But in this case, an electron will tunnel from one dot, then tunnel out here, and then go to another superconductor and make this loop over here. So this possibility, this coupling to semiconductor, allows to implement single qubit gates and 2-qubit gates and couple 2 qubits.
So that's equivalent to the braiding that you were doing?
Great question. I'll answer it in one more slide. So what I said in words, one can just follow the algebra and basically recalculate this using second-order perturbation theory. And what we can show that there is a shift of the energy level on this quantum dot, and this shift is proportional to the parity gamma 1, gamma 2. And therefore, if there is a shift of the level on quantum dot, and if I can couple to this quantum dot, I can read off what is the parity, even or odd, encoded in this Majorana pair. Okay, so how can we do it? And here's one way of measuring. So, one can just calculate the curvature of the level with respect to the local gate voltage on the quantum dot. This curvature corresponds to capacitance. So, different quantum capacitance of the semiconductor island will correspond to different parity encoded in this pair. So, coming back to the braiding. So mathematically, braiding transformation corresponds to this operation, R12. So it's just the product of gamma 1, gamma 2. So if our measurement scheme implements this operation over here, then we are set and we can do the braiding. Now, in order to do braiding, we cannot just have 4 Majoranas. We need to create a more complicated object which consists with an additional ancilla qubit, gamma 3, gamma 6, for example. Okay? And this ancilla qubit, if you have 6 Majoranas on the island, so the same idea, you have 3 wires, and the bridge which connects all of them allows you to already do certain manipulations which lead to braiding. So what is the sequence of operations is the following. So I mentioned that there is a way to measure parity of a given pair, say gamma 1, gamma 2, gamma 3, gamma 4, okay? And this projector corresponds to basically measurement of parity. And now you can see that certain sequence, and I show here, and you can just substitute these explicit operators here, that this sequence of measurements is actually proportional to this operator, gamma 1, gamma 2. So the sequence of measurements that one could perform on the system will be equivalent to braiding transformation. So the idea is not to move particles around, but actually perform a sequence of pairs, measurements here, here, and then here. And just these 4 measurements will give you the right outcome. So that's how we envision topological quantum computation. We think that we can, if we realize the system, we have ground state degeneracy, we can implement single qubit operations which consist of measurements, say, gamma 1, gamma 2. And suppose we think about measurement of gamma 1, gamma 2 as a sigma x operation, then the measurement of gamma 2 and gamma 3 does not commute with operator gamma 1, gamma 2, so therefore it has to be something like sigma z. So one can implement sigma x and sigma z operations, single qubit operations. They're not commuting with each other, so that's exactly what I explained before. And then one can implement even more complicated operations, which are exchange if we perform more complicated sequences. And in the paper that we posted, we also explained how to do 2-qubit gates and how to realize all Clifford operations. So I have to mention one caveat in this approach. So these Majoranas are the simplest examples of anyons. It's called Ising anyons. And the number of non-commuting operations that we can do with these anyons is limited, is not dense enough. So with this approach, we can only realize Clifford algebra, but the idea is that these Clifford operations will be exact, that one will not have to do error correction on them, ideally. So how do we make things universal? Because we want to realize universal quantum computer. In order to do that, we need to add one more operation, and that's just pi over 8 phase, pi over 8 rotation. So once we do this non-universal operation, then the system will be equivalent, this approach will be equivalent to universal quantum computer. So this usually can be done either by coupling to some conventional qubit or by doing some non-protecting operations within the scheme using finite splitting between Majoranas. And the advantage of this approach is still enormous over the conventional quantum computing because we're just adding one non-protecting operation to the system. And actually, there are very good algorithms to do error correction. They're called magic state distillation. And so the idea is that one can use these exact gates, Clifford gates, to do error correction of this noisy pi over 8 gate. So we still think that this approach is in principle much more, has advantage over the conventional quantum computing. We also pursue other approaches in which we try to realize this missing gate, pi over 8, using certain changes of topology of the manifold. So far we used planar manifold, but there are certain things that we can do by going away from the planar geometry. And in that case, one can realize also universal quantum computing without using these unprotected pi over 8 gates. So that's what the status of situation is. So the last thing I want to mention is what is the phasing of these Majorana-based qubits. So far, I was talking about idealized case in which the splitting between these two zero energy states is exponentially small, and we can basically set it to 0. But experimentalists in the audience can ask, well, look, your wires are finite. They can be up to 5 to 10 microns. So can you show me that in that limit you can achieve what we advertised? Okay. So for that you need to study what are the dephasing mechanisms and what are the processes lead to the sort of dephasing of Majorana-based qubits. So we've done this, and actually, just a side remark that this is rather non-trivial question because it has to do with understanding what is the charge of a quasi-particle in superconductor. And in order to answer that question, one has to go beyond BCS mean field theory, and I can explain the details how we did it, but I just wanted to summarize the result using this table. Okay? So in this table, we included the most common mechanisms for noise in systems: charge noise, phonons, thermal excitations. And it shows you what is the expected T2 time, so dephasing time, as a function of the length of the wire in units of coherence length. And you can see that advantage really happens when you have, L over Xi of the order of 20. Because in that case, this is the limit that's difficult to achieve with comparable circuits of superconducting qubits. And if you make it even larger, then, of course, exponent really helps you a lot. So what are the requirements in terms of the length? So if you take a coherence length of the order of 250 nanometers, then the wires longer than 5 microns will have this T2 star larger than 100 milliseconds. So this is the target that we are trying to achieve. We're trying to go to these wires that are longer than 5 microns, and we're trying to realize these Majorana box qubits, which have ground state degeneracy and many zero modes in these islands, and couple them together. So that's basically the end of my talk. If you are interested, I listed some review articles that might be very useful for graduate students and also faculty not familiar with this field. And with this, I welcome questions. Thanks for the attention. Yeah, so we know this because the orbital induced Zeeman field, which depends on the radius of these wires, for a given radius is larger than the required critical value. I mean, the orbital effect scales with radius of these wires, and by tuning the radius, using the right size, right diameter of the wires, one can, tune the Zeeman field to be in the right. Yes.
I have a question about the architecture. So you have these wires which sit in sort of rows, and can you couple qubits or whatever two-level systems that sit, beyond nearest neighbors?
In principle, yes, but that will require to have cavities. So if you have cavities, like cavity QED experiments, then in principle you can couple them non-locally. So that would be one solution to the question that you're asking. Yeah.
You showed some data for the zero bias analysis. Do you know of any simple, or I'm not necessarily simple, but test that an experimentalist could use to show that these zero bias conductor states indeed come from the Majoranas and not from some other gap states?
Right. So basically, what I said is that if you have these Majorana-induced zero-energy states, that they have to be robust with small, with deviations of parameters. As long as these deviations do not collapse the gap in the spectrum, then you should find the state to be stuck there at zero energy, because that's the whole argument. Now, if you have some other accidental state that for some values of parameters sit there, then small changes of these parameters should in principle move the state away from zero energy. And I also showed you that, and especially if it's like some tunnel gate which changes electrostatic environment at the end of the wire, then if you appreciably change tunnel gate, then in principle this state should move away. And indeed, experimentally, you see lots of crossings. And this would be an example of accidental state, but if you tune some parameters, this crossing, basically you see that it's some crossing and the level is not stuck at zero energy. And that's a way to distinguish. Now, but the second mechanism that I also explained, this exponential dependence on lengths, is even more convincing because it tells you that, well, it's not some local state that appears at one end of the wire, that actually the state depends on the whole length of the wire. So that's, in the same system, you see the same effect that, increases our confidence that we see the right physics.
So what controls the coherence length?
What controls the coherence length? So, okay, coherence length is controlled by microscopic parameters such as spin-orbit coupling, gap in